Hey, so in this supplemental video, we're going to go through the basic proof of why the integral test works for determining whether a series converges or diverges. So just remember, in order to use the integral test, our series function, or the analog for it in its more continuous form, must satisfy three conditions. That function needs to be positive, it needs to be continuous, and it needs to be decreasing. So that to say, if we have some series of a sub n equals 1 to infinity, we create that function analog, f of n. That is, whenever we evaluate that function at any positive integer value, we're getting the exact value back for that particular indexed term in the series. And we require that it's three things: positive, continuous, decreasing. So we'll see where those ideas pop up in the proof in order to make this work. So let's just go through kind of the basic steps of what we're going to do. We're going to go through three major steps to prove why the integral test works. The first thing we're going to do is make a connection with the left-hand rule and right-hand rules from integration. The next thing we're going to do is two cases. One case, we're going to assume that the improper integral converges and basically see what that gives us. We're going to see the popping up of one of our friends from sequences, the Monotone-Bounded sequence theorem. And then in the other case, we're going to assume the improper integral diverges and basically ask ourselves, what does this say in this case? So those are going to be the three basic steps that we're going to go through. So let's jump into it. So for any series, say the series a sub n, we are adding up an infinite amount of terms. And the first thing we're going to do is, well, let's start thinking about what types of functions we're allowed to apply integral tests to. So the first thing, we need functions that are positive, okay? We need functions that are continuous. There are no holes, there's no divide by zeros, things like that. The third thing, though, is what I want to focus on right now. We're considering functions that are decreasing. So why is decreasing something special? So let's focus in on this. Well, if we're to draw that function f of x as a decreasing function, we could generally write it as something like this. Some function that is obviously going down, but must stay positive above the x-axis. And for that matter, it's continuous. All right. So in general, this is our decreasing function. Now let's make that analog, or the connection, with our left-hand rule and right-hand rules from integration. So remember, for the left-hand rule, what we would do is we start on the left side of the function, and then we march to the right until we hit the next box. So if we start dividing these up in our rectangular fashions like we've done previously in calculus, basically what we'll see is when we find these boxes for left-hand rule, we would start on the left side of the function and basically march to the right until we hit the next box. And we would keep making this over and over like this. Okay? And then when we're approximating the area under the curve, we're really considering the area of all those rectangles. Now, the big thing that I want us to recognize here, of course, we have rectangles in this region as well, is we have in each of these cases, we have this over kind of estimate of the amount of area in each of these cases coming from left-hand rule when we're approximating the area under a decreasing function like in this case. All right, we'll get into that in a minute. Let's do the same thing, but for right-hand rule. Well, right-hand rule, we do the opposite. We start on the right side of each of our boxes, and then we march to the left. So for right-hand rule, we would start when n equals 2, or when x equals 2 in this matter, and march to the left. And we would do the same thing in all of these cases as well. And what you'll notice in this case, of course, in this region, since we're just saying, hey, we're going from 5 to whatever n is, there'd be rectangles there as well. But in this case, we're basically going to see that we have an underestimate of the amount of area under that curve. So everything I'm highlighting now is sort of our underestimate involved with the area under the curve. So with right-hand rule, we have this underestimate. And for left-hand rule, we have this overestimate. Well, this idea will come in handy next. So let's actually see what left-hand rule and right-hand rule are giving us. Now, in both of these cases, we're basically, well, we're not going to consider this last box here for left-hand rule for that matter. We're really just going to consider what happens if we end the integration up to this point. So up to x equals n. So in other words, we're only going to be really considering the integral in this case up to n. And of course, this is math. So what we're going to eventually do is take, the limit as n goes to infinity, introduce the improper integral through all of those steps and all of that jazz. But for right now, we're really just looking sort of at this integral, say 1 to n of f of x of our function. Now, the first thing I actually want us to look at is what's happening with right-hand rule. And well, with right-hand rule, if we look at all the areas under the boxes, remember the values that we're taking in this case. We're using the value of the function at 2, the value of the function at 3, the value of the function at 4, at 5, all the way up to n. So we're not actually using the value a1 anywhere. All of these values are really the values of those series terms, a2, a4, a5, an. So what we're really doing, because these these widths are all of unit 1, when we add up the area of all these rectangles, we're really just going to be adding up all of those terms, a2 plus a3 plus a4, all the way to an. So from right-hand rule, let me just write this out so we're clear. Right-hand rule. What we're really saying is I'm adding up a2 plus a3 plus a4 plus a5 all the way to an. I'm just going to slide that integral over. And what we recognized before was this was an underestimate of the overall area under that curve. So we can write that summation from a2 to an is less than or equal to what the actual integral is of the area under the curve from x equals 1 to x equals whatever n is of our function f of x. And we can do the same exact thing for left-hand rule. A few things to note for left-hand rule, though, is of course, we're using all those values on the left side of each of those rectangles. So we're actually only marching up really to the n minus first rectangle. But all those values are a1, a2, a3, a4, a5, and a sub n minus 1. And of course, each of these widths are still equal to 1 because we're just considering basically x equals 1, x equals 2, x equals 3, and so on. So when we're considering the area approximated by those rectangles, it's really just going to be the sum again of a1 plus a2 plus a3 plus a4 plus a5, and so on and so forth. But in this case, we noticed that that was an overestimate of that actual integral from x equals 1 to x equals n. So we would write this as, in this case, we have the integral from x equals 1 to x equals n of f of x dx, and that's going to be less than or equal to the sum of a1 plus a2 plus a3 plus a4 plus a5 all the way to n minus 1. So we're seeing that connection with left-hand rule, right-hand rule, and basically where we're seeing these overestimations and underestimations just based off of our series so far. So remember, the important thing for right now, we're estimating the area under those curves from x equals 1 to x equals n using either left-hand rule or right-hand rule. And in some cases, we're seeing an overestimate, like in the case of left-hand rule. But in the other case, we're seeing this underestimate, like in the case of right-hand rule, just using those rectangles under the curve. And this brings us to basically step 2, where we're going to start assuming that something about these improper integrals, whether it converges or diverges, and seeing the consequence of that type of assumption on our infinite sum or infinite series that we're considering. So the first case we're going to consider now is basically what happens when the improper integral converges. So that means we're now considering the full improper integral from x equals 1 as x goes to infinity of f of x dx converging. And again, we're assuming that this improper integral converges. And what we're hoping to see is what that implies about our infinite series. And you may have guessed it, we're going to use these types of inequalities that we just thought about above. So let's see what we have so far. Well, if we're going to start off using basically this idea from right-hand rule. So I'm going to write this again down below. A2 plus A3 plus A4, all the way to AN. And we saw that was less than or equal to our integral from x equals 1 to x equals n of our function f of x dx. Now, if we're considering the full improper integral, that is, we're integrating all the way towards infinity, what we can then say is, well, this integral that we had considered before from x equals 1 to x equals n, well, that must be less than or equal to the full improper integral from x equals 1 to x going towards infinity. And mind you, we just assumed that that integral converged by our assumption. So what is that telling us so far? Well, we're going to do a nice, a fun thing in a second, because basically what we're going to do next is try to show that as we keep adding on more and more of these a sub n plus 1, a sub n plus 2, a sub n plus 3, and we keep adding on to those approximations, that we're going to still see something that is less than or equal to that improper integral on the far right side. So the next thing that I want us to think about really fast is just a reminder that if we have a sequence is bounded and monotonic, then it converges. So let's make this connection right here. So we're basically going to look at a sequence of the partial sums of this above infinite series. And we're going to show that this sequence of partial sums is both bounded and monotonic, which will then imply that our series itself will have to be convergent. So where we're going with this, as a quick spoiler, this bounded idea, the upper bound is basically going to be that improper integral that's convergent. The lower bound, we're going to get help with, because we know that, well, this function f of x that we're thinking about, what we assumed by that function f of x was that, well, it was continuous, it was decreasing, but also that it was positive. And because it's positive, what we get to then say is, well, this sum that we're thinking about has to be greater than or equal to 0. So this lower bound we're basically getting for free, just based on properties of that function f of x. And because of that, our sum A2 plus A3 plus A4 to whatever A sub n value we want to go to, or n value we want to go to, it's going to be greater than or equal to 0. So the next step that we're going to do for this is basically grab this previous line going to come down here. Oops, looks like a square bracket came along for the ride. And basically to give us this entire series, we might note, well, in this case, there's a couple terms that are missing in that we only have A2 to AN here. So what we can do is just add an A1 to every side of this inequality. So just sneak in some of these A1s now. And then finally, could have probably done this in a little better way, but we're just, adding A1 to every single thing here. The inequalities still all hold since A1 is some positive number, since the function it's coming from has to be positive. So at this junction, if you remember, this idea of A1 through AN is what we call the nth partial sum. And what we're really thinking about now is, well, if we keep taking more and more higher partial sums, so instead of just, for example, S4 would be equal to A1 plus A2 plus A3 plus A4. S100 would be equal to A1 plus A2 plus A3 plus many, many terms in the middle, plus A99 plus A100. And we could keep doing this for more and more higher partial sums. But what we basically just saw was as we go for Sn, and we take that limit as n goes to infinity, that it's still going to be less than or equal to the integral, need to add A1, plus the integral from x equals 1 to n. And again, we're going to be taking that limit as n goes to infinity of that improper integral. So in this case, we saw that it's bounded by everything here. And of course, when we actually do this, this will be equal to, well, A1 plus the improper integral from x equals 1 to infinity of f of x dx. So we saw that it is bounded above by that improper integral that we assumed at the beginning of this second step converges. But we also know that this has to be greater than or equal to A1. So because of that, we have this sequence of partial sums converges. So therefore, the series itself must converge. So I really mean the sequence Sn from n equals 1 to infinity of partial sums so the original series must converge. In putting this all together, what this really said was, the way we started the second part was assuming that that improper integral converges. And we saw the consequence of that assumption. Assuming that improper integral converged necessitated that the sequence of partial sums converges, and then our series also converges. So we figured out the case of why, when the improper integral converges, our series also converges. Now we just have the other case to consider. What if that improper integral diverges? What is the consequence of our series in that case? So let's go to number 3. So in number 3, we're going to assume now that the improper integral diverges. And again, we want to see basically what happens as a consequence to our series in this case. So let's take a look at what we had earlier from left-hand rule. So coming back from left-hand rule, just go ahead and grab this and take it along for the ride. Now from left-hand rule, what we saw was for our integral from x equals 1 to x equals n, we saw that that is less than or equal to, well, the n minus first partial sum. So the other thing I want us to recognize here is this integral, we don't really know anything about right now, but we know something about an integral that's very similar to it. In fact, it's improper, the full improper integral. So for example, what we know is from our assumption up above is that the integral from 1 to infinity of f of x dx diverges. So what this implies is that as n goes to infinity, the integral of 1 to n f of x dx, this must go towards infinity. And we know that must go towards infinity because the function f of x is a positive continuous function. So we're guaranteed that this happens since f of x is positive. Okay, the other thing for us to note in this case is, well, coming back to our inequality that we had before. We're basically going to use that inequality and this idea we just thought about. From left-hand rule, we really have the following. The integral from x equals 1 to x equals n of f of x is less than or equal to our n minus first partial sum, which I'm just going to write as the following, from n equals, or let's, I guess we have to use a different letter now as our index because we have n as sort of the nth partial sum term. So let's use j, say j equals 1 to n minus 1 of a sub j. So just a different index with the same meaning. But we know that this is equal to the n minus first partial sum, which we can call Sn minus 1. And basically the only thing left is to say, well, as n goes to infinity, we know something that happens. As n goes to infinity, we know this thing is going towards infinity. So what that implies about this right-hand side is, well, if this right-hand side is always positive and is always greater than or equal to this integral between x equals 1 and x equals n, as n increases, well, this whole right-hand side must still maintain that same inequality, that it's greater than or equal to the left-hand side. So as n goes to infinity, what we then get is all of these partial sums must just keep growing and growing. So as n goes to infinity, our nth partial sum must also go towards infinity. And therefore, our infinite series diverges. So this is how we saw the consequence of what happens when that improper integral is divergent, it inherently implies that our series must also diverge. So in this case, we're basically able to say, hey, based with left-hand rule, approximating our integral, and just seeing how that left-hand rule relates to our series as before, basically just the sum of the first n minus first terms, we saw that that must be greater than or equal to kind of the integral between x equals 1 and x equals n. And then as we kicked n going towards infinity, that inequality was maintained. So we saw that the partial sums just keep getting larger and larger and larger. In the second case, or in the first case we looked at, where we assumed that the improper integral converged, basically what we were able to do is create a sequence of partial sums where that sequence was both bounded below by a sub 1 and bounded above by a sub 1 plus that improper integral. And because we know that all the terms of that sequence, or all the terms of the series, excuse me, are positive, that by going from S4 to S5 to S6, that the partial sums are always increasing. Tacking on the next term is always going to give us one more than the previous partial sum. So we're able to create a sequence of partial sums that was bounded and was increasing, or monotonic. And because of that, we could say that the sequence of partial sums converged. So thanks for checking out this video about the integral test.